In Part 3 of Lecture 4, we will discuss multithreading and multicores. As we have said, the concepts of resource allocation and dispatching unit have traditionally been embodied in the single concept of the process, that is, as a one-to-one relationship between threads and processes. Recently, there has been much interest in providing for multiple threads within a single process, which is a many-to-one relationship. However, as Table 4.2 shows, the other two combinations have also been investigated, namely, a many-to-many relationship and a one-to-many relationship. The idea of having a many-to-many relationship between threads and processes has been explored in the experimental operating system TRIX, spelled T-R-I-X. In TRIX, there are the concepts of domain and thread. A domain is a static entity consisting of an address space and ports through which messages may be sent and received. A thread is a single execution path with an execution stack, processor state, and scheduling information. As with the multi-threading approaches discussed so far, multiple threads may execute in a single domain, providing the efficiency gains discussed earlier. However, it is also possible for a single user activity or application to be performed in multiple domains. In this case, a thread exists that can move from one domain to another. The potential performance benefits of a multi-core organization depend on the ability to effectively exploit the parallel resources available to the application. Let's focus first on a single application running on a multi-core system. Amdahl's law states that speedup equals the time to execute a program on a single processor, time to execute program on n parallel processors, equals 1 times the difference 1 minus f plus fn. The law assumes a program in which a fraction 1 minus f of the execution time involves code that is inherently serial, and a fraction f that involves code that is infinitely parallelizable, with no scheduling overhead. This law appears to make the prospect of a multi-core organization attractive. But as figure A in this slide shows, even a small amount of serial code has a noticeable impact. If only 10% of the code is inherently serial, f equals 0.9. Running the program on a multi-core system with 8 processors yields a performance gain of only a factor of 4.7. In addition, software typically incurs overhead as a result of communication and distribution of work to multiple processors and cache coherence overhead. This results in a curve where performance peaks and then begins to degrade because of the increased burden of the overhead of using multiple processors. Figure B on the right side of the slide is a representative example. However, software engineers have been addressing this problem, and there are numerous applications in which it is possible to effectively exploit a multi-core system. It's been reported on a set of database applications in which great attention was paid to reducing the serial fraction within hardware architectures, operating systems, middleware, and the database application software. The figure here shows the result. As this example shows, database management systems and database applications are one area in which multi-core systems can be used effectively. Many kinds of servers can also effectively use the parallel multi-core organization, because servers typically handle numerous relatively independent transactions in parallel. In addition to general-purpose server software, a number of classes of applications benefit directly from the ability to scale throughput with the number of cores. Multi-threaded native applications are characterized by having a small number of highly threaded processes. Examples of threaded applications include Lotus Domino and Siebel CRM, or Customer Relationship Manager. Multiprocess applications are characterized by the presence of many single-threaded processes. Examples of multiprocess applications include the Oracle Database, SAP, and PeopleSoft. Java applications embrace threading in a fundamental way. Not only does the Java language greatly facilitate multi-threaded applications, but the Java virtual machine is a multi-threaded process that provides scheduling and memory management for Java applications. Java applications that can benefit directly from multi-core resources include application servers such as Sun's Java Application Server, BEA's WebLogic, IBM's WebSphere, and the open-source Tomcat Application Server. All applications that use a Java 2 Platform Enterprise Edition, otherwise known as J2EE, application server can immediately benefit from multi-core technology. Multi-instance applications. Even if an individual application does not scale to take advantage of a large number of threads, it is still possible to gain from multi-core architecture by running multiple instances of the application in parallel. If multiple application instances require some degree of isolation, virtualization technology for the hardware of the operating system can be used to provide each of them with its own separate and secure environment. Valve is an entertainment and technology company that has developed a number of popular games, as well as the Source engine, one of the most widely played game engines available. Source is an animation engine used by Valve for its games, and licensed for other game developers. In recent years, Valve has reprogrammed the Source engine software to use multi-threading to exploit the power of multi-core processor chips from Intel and AMD. The revised Source engine code provides more powerful support for Valve games such as Half-Life 2. The figure on the slide illustrates the thread structure of the rendering module. In this hierarchical structure, higher-level threads spawn lower-level threads as needed. The rendering module relies on a critical part of the Source engine, the world list, which is a database representation of the visual elements in the game's world. The first task is to determine what are the areas of the world that need to be rendered. The next task is to determine what objects are in the scene as viewed from multiple angles. Then comes the processor-intensive work. The rendering module has to work out the rendering of each object from multiple points of view, such as the player's view, the view of TV monitors, and the view of reflections in water. Some of the key elements of the threading strategy for the rendering module are listed here and include the following. Construct scene rendering lists for multiple scenes in parallel, for example, the world and its reflection in water. Overlap graphics simulation. Compute character bone transformations for all characters in all scenes in parallel. Allow multiple threads to draw in parallel. Designers found that simply locking key databases, such as the world list, for a thread was too inefficient. Over 90%, 95% of the time, a thread is trying to read from a dataset, and only 5% of the time at most is spent in writing to a dataset. Thus, a concurrency mechanism known as a single writer, multiple readers model works effectively.